Welcome to the American Physiological Society's Living History program. This program was initiated by the Society several years ago to develop an archival video record of senior members of the Society who have made outstanding contributions to the advancement of physiology as a scientific discipline and as a profession. My name is Professor Larry Kenny, and I'm a professor of physiology and kinesiology here at Penn State University. I have the pleasure today of interviewing my distinguished colleague, Dr. Elsworth Buskirk, who's an emeritus professor within the department at Penn State. Buzz, you have a very impressive CV, and your professional career really took off after your graduate career at the University of Minnesota. But I think people are always interested in the early years in a scientist's career and things that made them lean toward the development of a career in sciences such as physiology. Can you tell us about those early years before Minnesota?
Well, I was born and raised in Beloit, Wisconsin, and we lived on the edge of town, so I was able to get out and about in the wilderness around town, which I enjoyed. I also participated in a variety of sports there, and one sport that I thoroughly enjoyed was ice hockey. Winters were cold enough so that we had outdoor ice, and we had a city team, and I played for the city team, and that got me started in the athletic area. Always been interested in sports and also in science. And I was fortunate to have Beloit College right there. And there was a professor, an itinerant professor, who roamed the world, and particularly in the Gobi Desert, Roy Chapman Andrews. And he would come back from his expeditions and bring things, artifacts of one sort or another, and dinosaur eggs among them. And this stimulated my interest in science. So I think I went to most of his lectures when he gave them. The other thing was that was friends of the athletic director for Beloit College and his two sons. And so they had access to the gym there, and that worked out extremely well too. But then I had further ambitions to go on and enrolled at the University of Wisconsin in a curriculum chemical engineering. But that didn't last very long because World War II came on. And I was assigned to the ASTP program and was supposed to go to the University of Oregon for further study. We had the orders, but the orders were rescinded, and that was that. So on into the Army, and a voyage overseas of 28 days crisscrossing the Atlantic, submarines here, there, and everywhere, depth charges going off. But we finally got to England, and no damage to the ship. The only reminiscence that I have about the ship itself is called a Kungsholm, which was a brother ship, a sister ship, Gripsholm, which is a famous hospital ship at that time. Had an English crew, and the dietary intervention was Brussels sprouts and mutton. And we had that all the way from New York to England.
Have you had it since? Or
Pardon?
Have you had that meal since? Or
no, I haven't had that meal since, and I don't look forward to having it. And we were in England for a while, and then on to France and Germany, Belgium, Holland. And I had a chance there to witness the starvation that was going on particularly in Belgium and Holland. They were pretty hard hit. Of course, Germany was too. And those impressions of the civilian population stayed with me for quite some time. And then following that, I was commissioned overseas. I returned to the United States and enrolled at the University of Wisconsin again. But the University of Wisconsin was very crowded. And where we'd had 2 in a room before, there were now 6. And the first lecture that I went to in physics, they had a tape recorder rather than an instructor. Wow. So I decided, well, maybe a smaller school would be a little better, less hassle. So I went up to St. Olaf College because some of the local people had recommended it, and enrolled there, and dual major in physical education and biology, and became quite close to one of the professors there, a professor of botany. He wanted me to go into botany, but I resisted that, even though he was very kind to kind of set things up for me. I had read in the paper about the University of Minnesota and their starvation studies, and having observed starvation in its actual realm, I decided that I'd look into that. I first enrolled in physical education because that was very convenient, and I knew the director of the Minnesota program, Dr. Carl Nordley, but he steered me back into the laboratory for physiological hygiene. And this is where the classical study, the biology of human starvation, was conducted. And so from that point on, I stayed in the laboratory and worked there.
Before we get back to the University of Minnesota, you and I, over the past more years than we like to remember, have talked a lot off and on about sports. And you've always been very modest about your own athletic prowess and contributions. But in addition to hockey, you played several other sports. And I think the viewing audience would be interested in some of your trials and tribulations playing a variety of sports as a youth and on into college.
Well, the other sport that I contended with on more than a regional basis was in tennis, and had a doubles partner, and we always scored pretty high throughout the state in our doubles competition. I played #1 for, I think, 2 years at the Beloit High School, but in singles, and enjoyed that too. But we went further in the doubles competition than we did in the singles. In terms of the other sports, most of them are associated with an outdoor activity of some sort. And as I mentioned before, the chief one of those was hockey. Yeah.
Well, while you were at the University of Minnesota and immediately preceding the time that you got there, those were extremely exciting times from a scientific standpoint. As you mentioned, you came to the University of Minnesota well into the starvation studies that were going on at the time. Can you tell us a little bit more about what it was like to be there and some of the things that you were involved in related to that project?
Well, one of the funny things involved is that the biology of human starvation was essentially over. And so they were engaged in follow-up type of activities. The funny thing is that when I got there, one of the mentors, I think it was Dr. Taylor, who said, "Do you know anything about Leroy?" And I said, no, who's Leroy? I said, I know Kilroy. Kilroy was popular during World War II because everything went kind of haywire, you know, with Kilroy around. But Leroy, of course, is a drawing set. And so I was assigned to do some of the illustrations that were taking place in the follow-up studies from the biology of human starvation. The thing that impressed me most, I think, is the dedication of the faculty and how dedicated they were really to this world health problem at that time. And they were putting in all kinds of extra hours, working extremely hard. And this impressed me a great deal, and was really thought that, you know, this is an example that really sets it up as far as an approach to science is concerned, the way they have been going about it.
You spent most of your career doing research with human subjects. Tell us a little bit about the subjects in those experiments.
Well, the subjects I was involved with there were the students, of course, involved with the university. And the laboratory was based in the stadium. It was called the Stadium Laboratory. And you couldn't really tell it was a laboratory from the outside, but once you got inside, it was really very nice. And so the students came in and out regularly, and the people were responsible for teaching the basic course in exercise physiology for physical education. And I was involved in that almost from the start, first assisting one of the professors and then taking it on my own. The other sorts of subjects was military subjects. And I was responsible for going usually to Fort Lee, Virginia, screening a bunch of people and then taking them somewhere as a training program to set them up for what they were coming back to the laboratory to engage in. And we ended up on Mount Washington. There's a base camp there at Mount Washington, pretty good facilities, and we used that. And we were there, well, sometimes up to 3 weeks before we went back to the University of Minnesota with this entourage, and I usually was responsible for that part of the program. And that went on for the entire time that I was at Minnesota. Mm-hmm. Now, in terms of the dedicated faculty, we have a picture of a couple of them here. Here you see 3 of them. Francisco Grandi on the left, Joe Anderson, the biochemist, in the center, and Ansel Keys, who was director of the laboratory there. And an outstanding, all 3 of them are outstanding scientists. Mm-hmm.
You also did a lot of work with Henry Longstreet Taylor at the University of Minnesota, including some classic studies on criteria for true determination of maximal oxygen uptake, or VO2 max. Mm-hmm. Can you tell us a little bit about Dr. Taylor and about those studies?
Well, here's a picture of Dr. Taylor, not a very good one. He's at work here, making some observations on this fellow lying in bed. But he was a product of the Harvard Fatigue Laboratory, and had been with Keys there, and the 2 of them came together to really set up the program at Minnesota. Now, they had used something approaching the maximal oxygen intake in the study of the biology of human starvation, but they hadn't set up the criteria very well for how one determined whether you had arrived at a VO2 max, which is the maximal aerobic capacity. And so we decided to pursue that and work on this in a more detailed way. And so here we have a picture of the protocol that we ended up using. We ended up using a grade-related progression to increase the workload. Constant speed and 2.5% grade changes on the treadmill. And when we reached the upper region of this, if the change was not greater than 150 cc's per minute or 2.1 milligrams per kilogram per minute, then we decided that this was a good place to stop. It was practical, it didn't go on too long, and by the same token was very reliable, reproducible, and so we could do that. Now on the right here you can see the comparison of the detriment in the maximal oxygen intake that occurred when these various treatments had been administered. And everything from bed rest on to semi-starvation, all leading to decrements, and these decrements were progressive with time. Now, we wanted some indices to use here too, and we knew that in terms of the fitness of the individual for exhausting exercise, that the reference could be body weight. In other words, the amount of oxygen utilized per kilogram of body weight. But we also realized that there could be a separation here, and one could get this index in terms of cardiorespiratory performance. And so we used body composition techniques, mostly body density determination, to calculate the fat-free body weight, and we used that then as a comparative index for the cardiorespiratory capabilities. And both of these indices were utilized throughout a variety of studies. And the correlation between the maximal oxygen intake and kilograms of fat-free body weight was pretty high, about 0.885. We tried to refine this further and measured total body water. In fact, we had a cocktail that we used, the T1824 for plasma volume. We used the anti-pyramid space for total body water, the thiocyanate space for extracellular fluid, so we can manipulate the components of body composition to establish this. We did get a higher correlation with what we called active tissue, taking body water into account, but decided that for practical purposes, the two indices per kilogram body weight and fat-free body weight would satisfy the basic need.
As every exercise physiology professor and beginning exercise physiology student will attest, these really are enduring concepts, both the quantitative criteria for determining a true VO2 max, and then the standardization of maximal oxygen uptake values with respect to body weight, lean body mass, and so on. When you left the University of Minnesota with your PhD, you next took a physiologist position with the U.S. Army Quartermaster R&D Center. Tell us about some of the projects that you worked on there. First of all, perhaps how you ended up back in a civilian position with the Army, and then where the Quartermaster R&D Center was and what you were doing there.
Mm-hmm. Well, before doing that, perhaps we could go back and take a look at some of the relationships that were developed there at Minnesota, because these were carried on too at Natick. And of course, the director of the physiology program there at Natick was Austin Henschel, who had been a professor at Minnesota. So there was some continuity here. And this shows the basic relationship and between VO2 max and the fat-free weight. The big variable was the physical condition, really, of the subjects. In other words, this is an independent contribution to this. You can change this with an exercise regimen. The more strenuous the regimen in terms of training, the higher the VO max will occur. Then we found that if we related what we were doing with the semi-starvation and hard work with these soldiers, we found that the grip strength and the VO2 max kind of paralleled one another. And this is an illustration of that relationship. And of course, the longer the undernutrition goes on, why the more severe the deficit in these two variables. The other study, and this was kind of carried over too to the Natick work, is that we assessed complete water balances, looking at just about everything that we could at that time without some of the impressive technical advances that have occurred since. And we found that there was a variation in these variables for each one of the variables we undertook to measure, including what happened in the kidney, what happened to overall balance, what happened to plasma volume, etc. And this was carried over, as I indicated. And this shows the basic relationship between the I can't read that from here.
Oxygen intake
let's
and
go on
fat-free
to the
body
next
weight.
one. Now, in relation to this negative water balance, why one pays a price for this in terms of the elevation in body temperature and the heat, the stress that's put on the body as the negative water balance becomes larger. And these water balance studies were very definitive in this regard. They're hard to do. We find that a balance could be retained with about 1,200 kilocalories of work on a treadmill if they consumed about 1,800 milliliters of water. If we dropped it to 900, then things kind of went to pot, and we got this dramatic rise in body temperature. Now, this is a little different study that we conducted at Natick. We were doing quite a bit of work in the cold, and we used as a base for the field studies Fort Churchill, Canada. So we had a regular participation during the winter in laboratory activities there at Fort Churchill. And here we are interested in how much water do you lose from the lungs. And it became appreciable and it amounted to about 9% of the total energy turnover for the body, or about 32 milliliters of water per liter of ventilation. The higher the ventilation, the more water was lost. So that working in environments that were in excess of freezing, in other words, on the downscale from freezing down, let's say, to minus 40 degrees Fahrenheit, these relationships persisted, but you could lose up to a liter and a half per day just through respiration under these very cold conditions. Here we see that the work performance after dehydration, which we also conducted there, and a very profound loss with the dehydration. If we tried to acclimatize these people to heat, that didn't seem to have much effect. If we physically conditioned them, it did have an effect. The physical conditioned people were able to tolerate these kinds of studies much more readily than those who were left on their own or had been heat acclimatized without conditioning. Mm. So that was an extension really of some of the work that had gone on in Minnesota.
You're probably aware that there are currently people who are challenging some of these concepts in a very vocal way. Mm-hmm. Both the notion that dehydration leads to an increase in body temperature and the fact that dehydration impairs performance. And I think some of those people would do well to go back and read some of these classic studies that did such a great job with the tools available of documenting these relationships. Mm-hmm. So while you were at Natick, at the Quartermaster R&D Center, you also did some studies on sleep metabolism, did you not?
Yeah, we did quite a bit. And the reason I'm laughing is that, of course, one of the protective devices we've managed to build for ourselves was a sleeping bag. And the sleeping bags were constantly being refined. And we had a visiting scientist there who was an explorer. And so he took one of the bags under test and went to the neighboring community, and in a ditch by the railroad track, slept in that environment on a cold night. It was below freezing, but the cops happened to see him. And so they picked him up on a vagrancy charge. So this kind of stimulated a lot of activity in the lab. You know, everybody kept kidding him about this, and it went on for days. But in this Fort Churchill environment, and out in the tundra to the west of Churchill, we conducted a variety of sleep studies, and of course in the laboratory we did this too, because thermal protection, you know, for the soldier was very important in these environments, and the goal was to develop a better sleeping bag. So the results that we got, we brought back, and then the quartermaster took these and then went on to change their manufacturing processes to get rid of the cold spots and other things that went on. But these experiments were kind of interesting because people tolerated this quite differently. And some of the subjects we had adapted to this pretty well. Some couldn't undertake it at all, and decided that there were other things they would rather do. Mm-hmm.
Subsequently, you ended up, after your Natick years, taking a position at NIH.
Mm-hmm.
And there you were involved in a variety of different things. Your slide here that you just put up determines some of the differences and some of the studies that you had done. These are still at the Quartermaster Corps, right?
Military brass was interested in this project, and we were, they didn't design the study, of course, but by the same token, they wanted it completed because they had some problems both in the heat and the cold with the African American subjects. And so we decided to take a look at the differences in body fluids in these people, and found that there were some distinct differences, both in the lower plasma volume in the African Americans, lower blood volume, lower red cell mass, and lower hemoglobin concentration. But when we studied these people both in the heat and the cold, we didn't find any difference unless we ran across some subjects, which we did, with a sickling trait. And these people obviously had problems in these environments. But overall, we decided that there was no significant difference in terms of the African Americans and the white soldiers serving in these two distinct environments.
Mm-hmm. Mm-hmm. When you left Natick, you took a position at NIH. Mm-hmm. Can you tell us a little bit about that transition, what drew you away from Natick and into NIH, and then a little bit about the some of the unique experiments you were involved in when you made the move to NIH?
Well, we had at Natick had some very sophisticated chamber systems, and we could do a lot with those environments because you control temperature very well, humidity very well, wind speed very well, and so I was familiar with the work in chambers of this sort. And then I got a request from the NIH that wanted to put together a smaller chamber to measure the metabolic situation in a variety of different subjects and patients. So this transition wasn't all that great in terms of the chamber type operation. Now, one of the people who was at Minnesota, Olaf Mikkelsen, another biochemist, had the laboratory right next to where this chamber was going to be built. And it's my understanding that he played a role in my being contacted initially, to come down there. And I worked with the director of the scientific studies and arthritis and metabolic diseases. That was the institute we were associated with, Donald Whedon. And he, too, was interested in this and decided to put some money into the program. And I was brought in as a director of this facility. And now this is an overall diagram of all the things we got involved with this chamber. The other people in the program down there were interested in using it for their particular patients. So we did collaborative work with the variety of clinical people. And the goal was to measure total energy turnover and heat exchange under continuous measurement conditions. So many of these studies were of the order of 24 hours or more. And we used differences in exercise intensity, differences in the environment, cold versus heat, studied sweating and the various divisions, of heat loss from the human body. And these continuous measurements were attractive to a variety of people. And so we constantly had requests to do this or do that. The other basic thing that we did, we had a kitchen there which served whatever diet we wanted to administer to these people. Plus that, we had facilities for studying body composition and used this as a base reference. And we studied individuals in terms of their endocrine needs, and in terms of chronic conditions they may have had, and endotoxin exposure, for example. And so it was very interesting, and we worked hard, and since some of these studies were 24 hours a day, they were quite demanding on us personally, because go home after spending a day, take a few minutes off to eat a meal, and go right back to the laboratory and spend the night there. It's so from that point of view, it was a little bit different. And
Now, this unique metabolic chamber facility that you directed also has important historical significance, because it was the precursor to something that most physiologists are now very familiar with, which is what we commonly call the common metabolic cart. How did that all develop?
Well, that's true, because we had put together this, what you might call a maxi system, in terms of what others would desire as a mini system. The engineers from a couple of these companies were interested in developing these mini systems to use for other purposes. They came in and studied what we had done in considerable detail, in terms of all of the special calibration procedures that we used, and in terms of the transducers that we used to measure the various variables. And so they spent hours there going over this. And some of it also contributed to modifications that we made. But their goal was to put this in the clinical laboratory in terms of testing. And ultimately what did happen is that these systems were developed and were used for exercise stress testing for patients in cardiology, and also for testing by exercise physiologists for a variety of purposes. And they're quite common, still being used now. Mm-hmm. So this was an offshoot of what we had established here.
Tell us a little more about some of the studies using this unique chamber.
Well, this is in heat debt in relation to percent fat. And you see that the percent fat goes up while the heat debt becomes appreciable. These people don't respond with elevated heat production to any major extent. And then if we calculate the total body insulation, we find that it's a curvilinear relationship with heat production. That's what this particular illustration shows. Now this shows the type of metabolic determinations that we could do with this chamber, and we could follow just about everything that we needed. Way down in the bottom, we have the body composition changes, which, with the short transient time periods, don't change all that much, because for most of those changes, you need to get a difference of greater than about 2 to 3% in order to ascertain useful information, because they just aren't more precise than that. We studied nitrogen balance, and we studied exercise intensity, and we also measured fecal loss, urinary loss, and get a complete profile of whatever the experimental regimen was. Now this is a diagram of the system that we used, and you can see in the upper left-hand corner this a box that has been outlined with the patient in there. There was a treadmill on the inside, and we had pass-through windows so that we could get material in and samples out. And the instrumentation that was associated with this, that the others were interested in to develop their mini system. So this is kind of a crude diagram, but you end up with a big room full of equipment just to make the measurements that you're interested in on the particular patient that's inside. This is one of the studies that the cardiologists were involved with, and we spent some time on it as well. And was the measurement of the oxygen debt and people with cardiac deficiencies. They weren't in heart failure, but by the same token, they had past rheumatic heart disease. In other words, were compromised. And the oxygen debt with the administration of digoxin and the turnover in these people was significantly reduced on this digoxin. So they allowed these people to exercise at greater intensity than they otherwise could, with less physiological modification than otherwise would occur. Mm-hmm.
Do you have any more slides from this one?
I don't know if there's any more here. The body composition that we used there, we had a special, set up a special system because these obese people, we couldn't get in an underwater weighing tank and do a good job with them. There was just no way to do that. So we had a clinician there by the name of Nathaniel Berlin, who had worked out in San Francisco with a physiologist by the name of William Siri, and they had developed this helium dilution technique. And so we set that up at NIH. We had to modify it some, but this proved pretty a really good device for getting body volume in these obese people. The only problem was when we had something like 600-pound individual, they filled up the space in the measuring cylinder, really, that we developed. And if you get pockets of gas, you know, beyond the hips, whatnot, why the gas, the helium will not diffuse into those areas, so you don't get a true helium dilution for measuring the body volume. So this was a problem even with the some of the obese patients, but they had to be pretty big in order for this to happen. But we had to go to this device rather than the underwater weighing to do the body composition studies.
Mm-hmm. So from NIH, my favorite part of your history is your transition to Penn State, where you took a new academic position. Describe the nature of that transition and the position that you subsequently took at Penn State University.
Well, this was a hard decision to make because we were very active at NIH, and I thoroughly enjoyed working there. And one of the other advantages was you didn't have to worry about financing. Well, you had internal mechanisms for, you know, for designating dollars, but by the same token, the financing was there. You didn't have to be on the move constantly to bring in additional grant funds. I was approached by the people here at Penn State, largely Professor John Lother and the athletic director Ernest McCoy and the president of the university at that time. They wanted to set up a program in what you might call exercise physiology. And I had been up here 2 or 3 times because Penn State had a chamber here too, a total body calorimeter that was of interest to us in developing the chamber as we did at NIH. So I'd been up here before to look at this calorimeter, and it was distinguishable because you had to have 4 sheep, 2 people, or a bull in terms of the metabolic mass inside the chamber to get decent results. But this was what they called a total body calorimeter. You can measure the entire energy turnover for that biological preparation while it was inside the chamber. The means of measurements were not all that sophisticated, but by the same token, with a lot of hard work, it was very precise. So we had transferred that back to NIH. So I knew about that, and I knew the people involved, and had this invitation to set up a new laboratory here at Penn State, which we ultimately decided to do because of the school situation here, and you didn't have to worry about a lot of travel density. Mm-hmm. You can move around pretty well with really no constraints. 5 minutes here and 5 minutes there. That was the situation. And so they made an offer to me, and I decided to take it. And we set up what we called the Laboratory for Human Performance Research. And the reason that name was selected was because the people in biology and ecology of science felt that physiology as a program should have been in the College of Science rather as an independent laboratory. Now, the laboratory was agreed to be set up as an independent unit with a control for operations structured in graduate school. So they really had two people in the supervisory roles, the dean of the graduate school and the dean of the College for Health and Human Development. And throughout the years, these people got along pretty well, so there was never any conflict between these two. And we decided really from the outside we would stick with exercise. This would be one of the base operations for the entire program. And we did so until things began to change, and the structure was transferred to the College of Health and Human Development. So it was an opportunity to start a new program. We had a student body here that was fairly large, I think 17,000 at the time, and so there was a good subject pool, and that's what made the transition possible.
Did the graduate program in applied physiology begin at the same time, or did you first establish the laboratory?
We decided that we had to have basic science program and a home in the scientific community for our students. As a consequence, since there was no physiology program here, we got together with the people in biology and finally convinced them that this would be a good operation, and we did have students who wanted to come. And so we set up that, and so that was one of the first inter-college programs at the university. The other one extended that program at that time was in genetics. So genetics and physiology were the first two in that. And I think ultimately we ended up with something like 10 programs that, and I don't know what there are now, but
I think there are fewer than that now, because that trend has reversed itself a bit, and colleges control more of the graduate programs. But I think 10 was probably the maximum over the past 15 or 20 years. The building that you were housed in when you first set up the laboratory is not the Knoll Laboratory building that we're familiar with now. Can you tell us a little bit about where you were physically housed to create this new laboratory when you first came to Penn State in 1963?
Well, that was an interesting situation, because in Rec Hall there was nothing suitable at that time for the establishment of a laboratory, and the College of Science didn't have any additional space at that time either. So what was available was what was called the team room, which used to be under the old stadium that they had for football, and it was right in back of the Kern building. There was a parking lot there and the motor pool. They had their vehicles in there, and then we had the old team room. So we got sufficient funds to remodel the place completely. We set up some chambers there. We also set up a biochemistry laboratory and other testing type rooms for use for the exercise physiology. And that really worked pretty well. A one-story concrete block building under the stadium. The stadium was gone because they had built the new stadium, the Beaver Stadium, out where it is now. And we had that whole room. Plus that, we eventually had space in the old water tower, which was right behind this low one-story concrete block building, and also had space down at the other end of campus, what was called the Myra Dock Cottage, which was associated with health and human development at that time, but they weren't using it, so we used it as an additional laboratory. Plus, we put together a trailer, a furniture van that was refurbished on the inside, and that became an independent laboratory facility. And we backed that up behind the low building and used that for exercise stress testing and other things that we were involved with.
Well, the water tower is still here.
Mm-hmm.
The one-story block building extended its useful life even after you moved into a more modern facility. It became the motor behavior laboratory for a period of time when I first came to campus here with Dewey Morehouse and Bob Christina working in there. That building is now gone in favor of a parking structure. But in the early 70s, you started to see a vision for and design a new modern facility that became the Knoll Laboratory for Human Performance Research. How did that transition take place?
Well, really, it didn't start that way. We drew up some plans for expansion of this building that we had, and it was a kind of a tower arrangement on one end that would have given us 2 additional floors of space. And I approached the NIH because they had a facilities grant program at that time, and we managed to get some money to have that structure added to our laboratory. The university physical plant people and the administration decided that they had other plans for this area up here. And so they said, well, we don't like this idea of you adding to that old building, so why don't you consider another structure? And I said, well, I don't have money for another structure. And they said, well, we'll help you out in this regard. And so they paid the difference between what the new building would cost and what the old building, modification of the old building would have cost. So that's what happened with the development of the new lab. And we had a free hand in what was going into this new laboratory. We essentially designed it right from the start and got the facilities that you now have there in the laboratory, and I think it's worked out pretty well. The addition of the GCRC, this clinical research program, that addition to the building has added extra capacity and also made opportunities for other people. So,
what about the contribution of Robert Knoll and his wife Marie Underhill Knoll?
Robert Knoll was a patent attorney for IBM, and he had given money to the College of Engineering, particularly electrical engineering. His wife was a graduate of Cornell University and was interested in nutrition-related and public health-related programs. So it was his wife, really, who was a benefactor for our program. And Charlie Lupton, who was a fundraiser for the university at that time, had contacts with these people. And we got together, and together with the Knowles, and they decided that they would make some contributions to the laboratory effort here on campus. And, of course, associated with that benefaction was the naming of the laboratory, the Knoll Laboratory, which is really named after him, but the money came really from Mrs. Knoll, because she was interested in the type of programs that we were running. Mm-hmm. And a very nice lady, and very thoughtful. Came to the campus many times, and
I've had the opportunity to meet Mrs. Knoll several times during my early time here at Penn State, and she was a fantastic lady and a true benefactor to not only the building but also to some subsequent graduate student support for students coming through the laboratory, in particular women scientists coming through the laboratory. Tell us about some of the studies that took place from 1963 on during the early phases of your career at Penn State.
Well, we continued some of this work with the chambers, and when we measured people on a relatively long-term basis, and here's an example of a 2-hour exposure to 10 degrees, 50 degrees, 10 degrees centigrade, 50 degrees Fahrenheit. You see that a lean subject has on the lower level, very marked metabolic response to this 2-hour cold exposure. The obese subject on top, their variability is really around the baseline, and there's not much response at all. Now, there are a lot of individual differences here, but the role of body insulation and fatness is relatively profound. So we had a series of those studies on women. The other thing we did, the Olympics came along in 1968. They will be conducted in Mexico City, and people were interested in the training of individuals for the competition at this altitude. And some authorities like Roger Bannister in England said people are going to die, if they compete in long-distance events in that environment. And so there was an interest in studying the effects of altitude on the performance of track athletes. So we designed an experiment that took us from Penn State here to Peru, and we set up a laboratory down there in Nunoa, Peru, at a little in excess of 4,000 meters. Took our group of athletes that we studied here, studied them down there, and then we brought them back to Lima. And we went up to the top of Mount Evans with some of these people. That was a little higher altitude. He brought them back to Alamosa, Colorado, at about 7,500 feet of, and then back onto about Penn State. The goal was to study these people at these different altitudes and to see if there was any carryover in what training had been done. And we finally decided that Well, the training in Peru at 4,000 meters was too high, that one had to drop the exercise intensity too far to get effective training under these circumstances. The same was true of Mount Evans. At Alamosa, Colorado, the training could go on with just about the same intensity with a slight reduction with respect to Penn State. The carryover was minimal, really no real effects, and we came to the conclusion that the biggest variable at all was just the educational variable that needs to take place to modify one's pace of doing something, particularly in the distance events, so that the performance could be carried out. There were no hazards. We got no pulmonary or cerebral edema. The athletes down in Peru were able to compete with the local soccer players on an even basis, even though they were not really soccer players. But their status was pretty much the same as these natives at altitude, who lived and worked in that environment at all times. And they had to work there because it's a marginal living up there on the Altiplano. There are not a lot of resources for them to follow, not a lot of supply chains or anything else. So, this is a result of the reduction of maximal oxygen intake when going up there, and the elevation in ventilation volume. And you can say that when you come back to Penn State at the very end of this experiment, that not much change had been made. So that was the outcome. And we participated in a couple of conferences subsequently discussing these matters, and some plans were made for further work in this area. And of course, some of that has gone on and in recent years.
The modern concept of live high, train low.
But this was the first effort to try to look at the training techniques with respect to altitude exposure. And this shows the reduction that takes place in the maximal oxygen intake with altitude, and it's pronounced and it's reproducible. Mm-hmm.
There were some other studies that were performed at Penn State related to coronary artery disease mitigation and a number of other areas that you were involved in, some further body composition studies as well.
Well, this just shows the comparison of the athletes and unconditioned subjects, new sojourners at altitude, to the natives in terms of the maximal oxygen intake and the ventilation. And the other one is at a lower exercise intensity, showing that the athletes we took down there and the natives were just about on par. This is hard to interpret, but by the same token was kind of meaningful, because we got together with people at the University of Minnesota, the University of Michigan, and the University of Wisconsin. And the desire of the people at NIH was to set up a program related to the prevention of coronary heart disease with exercise. So we got involved in this study, and this rather heavily weighted table here shows some of the recruitment procedures that went on and why people participated or didn't participate in the study. And they found that, for example, the positive things. Smokers didn't want to participate. If the person was quite active, their chances of participation were greater. If they were married, the chances were greater. But such biological variables as cholesterol, blood pressure, other things that we now associate with coronary heart disease, these things didn't seem to make any difference in the recruit process, although there was a general impression that people who were approached by this felt that exercise really did make a difference. But their reason for participation varied quite a bit, and the factors were studied that in relation to participation were quite varied, and it was a very complex sort of thing. And the people at the University of Michigan really worked this out. Now, this study was really a pilot study because we wanted to see what the participation was after they had volunteered, after they were in the program, and how they would participate as the study continued. And we found that the dropout rate was about 50% at 6 months and remained relatively steady thereafter. And in terms of setting up the conditioning programs for these people, we have had a control group. We had an exercise group, and we had a volitionally active group, people more active than we could have made them. And our recruitment area here was the entire faculty and staff at the university here at Penn State. Minnesota was a telephone survey of the people in Minneapolis. Wisconsin, it was kind of half and half university, half community. And at Michigan, they really didn't have any participants. What they had was the basics schema of measurement techniques and other things in epidemiology that pertain to this study. So the study went on for a year, and we subsequently did a follow-up of 13 years of these same people, the ones that we could get back and measure. Study went extremely well. We could influence the maximal oxygen intake. Their fitness improved. Not much effect on the variables such as cholesterol, blood pressure, triglycerides, other serum lipids. The only thing that we saw was a slight reduction in preventricular contractions, which we picked up during the exercise stress testing, and they found the same at Minnesota. No difference in morbidity or mortality because the samples were too small. Now, since it was a pilot study, they went on to calculate how many people in a definitive study would be necessary. They came up with 24,000. So this was well beyond what we could do. And so the NIH people decided that they would go to a multi-factor study, and this multi-factor study was called Mr. Fit, which you've probably heard of, and that subsequently has gone on to other studies. So this was one of the first in this whole area. The other study of this kind was the study of the bus drivers and the people who took the tickets for the buses and that sort of thing in England, which had preceded in part this study, but they went on at essentially the same time.
These studies really provided some of the early underpinnings for what became modern cardiac rehab, cardiovascular rehabilitation programs in terms of predicting adherence and compliance of patients in those programs and what to expect with respect to improvements in functional capacity, risk factors, and so on.
Oh, that's true. Yeah. Yeah, it's one of the studies that has gone on for a number of years is the one down in Dallas, Texas. Cooper started it, and it was a kind of a clinical intervention study with really no follow-up with the results. But since then, some of the people who are interested in epidemiology have gotten a hold of these data and have come up with the conclusion that exercise really is a definitive factor in this whole area of prevention, and that one can be moderately overweight and obese, and if still as one is relatively fit, this becomes of significance, you know, in this whole ballgame.
Do you have more slides from Penn State studies?
No, we'll skip that. This is an additional procedure that we ended up with body composition as an independent reference for a number of things, and we wanted to get at the best base possible. So we had worked with the underwater weighing system for a number of years and refined that with helium dilution methods with the total body water, both tritium and deuterium for total body water. And that helium dilution method. And we decided to check some of these things with the colleagues at Brookhaven National Laboratory, including neutron activation for total body nitrogen and total body counting for potassium-40. And they came to the conclusion that these things did describe essentially what we wanted, and that we could depend upon the total body density as being of considerable usefulness, bearing in mind that we had this 2 to 3% variability that you had to deal with just because of the techniques. We went on to study creatinine metabolism and its effect on body composition, and also a label for the musculature 3-methylhistidine, and ended up using these two in an effort to get at what the muscle mass actually is. And so that's where these efforts ended, and now, of course, with the sophisticated counting machines that they have, that some of these things are not used that much anymore. They may be used for calibration purposes, but that's about it.
Buzz, you've mentioned a number of people who've influenced you over your career. Is there somebody that you would consider to have been your greatest influence?
Yeah, I think that that would have to be Henry Taylor at University of Minnesota, because we worked together. Well, I think the last time we got together was only a couple of years before he died. So I worked with him essentially from 1950 until about 1995. And he was I don't know whether you ever knew him or not, but tremendous individual, dedicated and excellent scientist.
This video will be available through the American Physiological Society website and through other venues. What advice would you give to a young person now who's currently starting out, embarking on a career in physiology?
Well, I think that the young people in this day and age, I think, are exposed to different things than we were when I was a graduate student. They have different types of education coming in. But by the same token, I think there is a real need for them to have the perspective that they get the best education in science that they can get. Now, if they want to supplement this in other directions, that's great. But they really need the tools in science. But nowadays, the tools in science are changing so rapidly that it's hard to keep up with this. The personal connections are so important as well. In other words, getting a good advisor, someone that you are compatible with and can work well with and take advantage of the opportunities that they have because they have more money or because they have some technical assistance, or they have other things that you need really to go forward. Then there is a need to keep abreast, really, of the changing techniques in whatever area you choose to concentrate on, and to keep abreast of those techniques so that you can use whatever best fits for the experimental setups that you feel that you need to use. I mentioned the ancillary personnel as well, particularly the technicians, because they play such an important role in getting a person started in terms of use of the actual equipment, and they need this type of help as well. So they need a laboratory, if possible, that has this base of operations that they need. The other thing is that to have exposure to others working in the same area, and this is best accomplished by the mentor, whoever, or other people in the department, bringing in speakers that are of interest. But the other thing is that they have professional meetings, and as a consequence, an organization like APS becomes home to these people scientifically. This is their base of operations, and the contacts they make, and in these professional meetings has a bearing on all aspects of their career. So that's important that they become affiliated with these as early as possible in their career. And of course, the problem of money and being well supported, one has to look for those opportunities as well. And this again goes back to the mentor to help provide this for the graduate student, and the graduate student should look for this assistant. And in certain instances, they are recruited by the faculty member, the mentor. Others are not, and they have to look around for this independently.
Physiology has, over the past 30 years or so, followed some trends, upward and downward. You and I have spent most of our careers as integrative physiologists. There's always a danger of losing that integrative approach by becoming too reductionist. And I think now, thankfully, the pendulum's swinging back toward integrating physiological systems approaches into our understanding in the discipline of physiology. What do you see as the future of physiology in the American Physiological Society? Can you gaze into your crystal ball and predict over the next 50 years what you see happening in physiology?
Well, that's a difficult difficult to answer because there are so many things that can change. But by the same token, I think you've hit on a very important point. This integrative concept is important. I always like to think as that men and women are made to move and not to rest, so that this gives one a different perspective in terms of the integration than just studying resting physiology. By the same token, if you transfer down to the organ level, the integration becomes from the technology to the cell, to the control mechanisms that are going on, but ultimately the liver has to function as a total organism. It doesn't function just independently, depending upon one little cell, that may be disoriented. So I think the concept is that in terms of change and in terms of preservation, this integrative concept is important, will always be important, because you have to take what the cell and micro physiologists come up with and translate this into a larger system, whether it be organ, whether it be the total organism. And I think that has to be preserved. We just have to preserve that. And
so you feel that the future's bright for aspiring young physiologists just starting off in their careers?
I think so. There's no end of problems to work on, and I think this is illustrated by the expansion, of the journals, and now with the automatic data transfers that occur and the publications that occur in the computer realm. Why this transfer is even more rapid than it ever has been, and there's so many sources of information now, and the publications still keep coming out. New ones coming all the time. It's amazing.
Well, thank you very much for your time. It's certainly been a pleasure for me to have this opportunity to have this conversation with you. You and I have been associated for about the past 28 years or so, and I look forward to the next 28.
Well, it's been a pleasure, and I'm wishing you the best of luck in terms of continuation of the activities that have gone on in the past and will continue in the future.
Thank you.